Okay, welcome OCGS members to the April technical luncheon. Appreciate everybody that could join us today. Please, as always, thank our sponsors for providing support to the society and helping us put these things on, and classes that are coming shortly to us. I just want to call your attention to a couple of events for May 19th. Jeff May will be speaking to us at our luncheon using sequence stratigraphy to optimize target selection in unconventional reservoirs. So that should be a pretty interesting talk. And then we're going to have our first in-person class for OCGS members and non-members. May 26th, 27th, and 28th. It's reservoir engineering for geologists. If you need more details, you can check it out on the website. Okay, now for the man of the hour, Dr. Stephen Hubbard has graciously agreed to speak today. He's the associate professor with the Department of Geology or Geoscience at the University of Calgary, and he's an AAPG Distinguished Lecturer for 2021. He'll be talking to us today about deep water channel processes and products. And let me give you a brief bio on Dr. Hubbard. So Steve Hubbard joined the faculty of the Department of Geoscience in 2006, shortly after completing his PhD at Stanford University. Prior to his PhD, he obtained his BS and MS degrees at the University of Alberta, and has worked as a geologist for Shell Canada. His research, teaching, and student mentorship is focused on topics in stochastic sedimentology and stratigraphy, as well as applications to petroleum geology. He specializes in processes and products of channelized depositional systems. So thanks again for joining us, participants, and thank you, Stephen, for giving us the talk today. So I'll hand it over to you now. You can share your screen. I will mute myself.
Excellent. Thank you for the introduction. Hopefully my screen looks good to you. I'll let somebody chime in and tell me if not. It's a real pleasure to always have a chance to talk to you about something that's near and dear to my heart. I love talking about deep water sedimentary systems, and through today's talk, as you can see, entitled "What Processes Control Widely Observed Patterns in Deepwater Channel Fill Stratigraphy." It's kind of a journey that I'm going to talk to you about over kind of the last 10 years, thinking about some work I've done in outcrops, and then being inspired by some new ideas from seafloor surveys and so on. So a picture here is from a place called Butte Inlet in westernmost Canada, in British Columbia, a fjord where I got a chance to monitor some modern turbidity current systems, as I'll describe. And so the deep water, this is really in many ways a sedimentology sort of story, building towards some implications for what it all means at the end. But I think, something, we may or may not think about that often is deep water systems are generally poorly understood, or have been historically. And it wasn't until the 1970s, which really isn't that long ago, that we really started to put together kind of basic models. One on the left from seafloor surveying and on the California borderland, one on the right based on outcrops in Italy. And what's fascinating about these, in many ways, we usually do think of the modern here on the left being the key to the past, a model there on the right. But in the deep water, it's not so simple, because these environments are largely inaccessible, and that in a lot of ways has left us with a lot of opportunities to in more recent times to really shed light on how these depositional systems work and what those implications are then for things like reservoirs in deep water systems. Again, I guess maybe it's all relative. You see these numbers in the mid 80s. Again, to me, that's not that long ago. But some of these images from the seafloor, these are from the seafloor images from Amazon fan. And these came out in the 80s, and the images kind of, I think, shocked a lot of folks. I mean, these look, these sinuous channel forms look more like rivers at the bottom of the ocean as part of the Amazon fan system. And you can imagine, without having seen these before, it was probably not what we were expecting. Going back to these more simplistic ideas, we assumed there was channels, but Did they look like rivers? And so, it's these kind of questions, data and technology improves, you kind of get more inspired and more ideas about what we might expect to see happening in the bottom of the ocean, but then, of course, how that might be manifest in the rock record. And once we understand that linkage, we have a much better understanding and ability to predict and delineate reservoirs and so on in these deep water systems. And so I start by thinking of rivers. And this is this is the kind of technology that's easy these days. Google Earth Engine, you can go and see repeat surveys. You can watch rivers evolve through time. Think about the bars that they leave behind. Think of and not just think about it, you could go here and punch core holes into the surface, vibrocores and so on, calibrating what we see happening here with some deposits. And of course, for me, that's another aspect of my work that I'm not going to talk about too much today, but I have had the fortune of doing exactly that, looking at understanding fluvial reservoirs by taking all sorts of vibrocores and then tying them back with the central driver to link our models to what we see in the rocks. And I think we're all really familiar with something like this in fluvial systems. You got a point bar model. On the left here, you got a point bar accreting. The channel is eroding on the right, and these two things, this erosion and deposition, work in kind of equilibrium to leave what is an elegant and predictable product here. What is elegant, I should say, is the facies model. Very simple, yet very descriptive of what actually happens. But that isn't always the case in all systems. But boy, does it ever help us when we look at fluvial systems in the subsurface. And this is an image from about 400 meters below the surface here in northeastern Alberta. I am, of course, here in Calgary today, and I'm looking. I looked at these data a long time ago. This is a time slice about 10 meters from the top of the Athabasca oil sands reservoir, so Cretaceous continental river scale system. And I think you can spot pretty readily some of the big point bars, kind of the Oxbow Lake fills. And if there was any ambiguity about how we might predict facies based on these last images or ideas I showed from navigating modern systems, that ambiguity kind of goes away when you look at what I've overlain here are all the wells that have been drilled in this area. And so you see the scale bar on the lower right. These are all pretty tightly spaced wells, and most of them have cores through this interval. So a lot of calibration is available. So from observing the modern system over time, standing on the banks of the river, measuring currents, taking vibrocores, through to then taking ancient data sets like the one you see here, it's a pretty full circle where you're pretty comfortable in understanding and delineating a reservoir such that you can optimize production and make the most of any asset that is in a similar kind of setting. That is not the case in a deep water. Primarily because we just have not been able to monitor these deep water systems. Flows are sporadic. They're immense, and when they do occur, they often destroy any sort of devices we put down in the bottom of the ocean to try to measure them. So it's been a real challenge. And so my objective today, though, is to take a look at links between submarine channels and the seafloor, because there are a lot of new data coming out based on new technologies and their products in the stratigraphic record. And I'm going to do that visiting outcrops that I've been fortunate enough to look at over time. So as I said, I'm going to kind of walk you through a bit of my personal journey. And that personal journey comes with collaborations with so many students and colleagues at different companies and universities over the years. But I'm going to start by thinking of outcrops, observations we've made, really confident and comfortable with the observations. But as I'll show you, there's so many unanswered questions about what we're observing and how it formed. And then I'll head to that Butte Inlet submarine channel system that I briefly showed a picture of at the start from Western Canada. Get a whole bunch of new ideas, things I had never thought about before, and most people hadn't, just because we didn't have the data to be inspired by, if you will. And I'm going to take what I learned from Butte, and I'm going to head back to the same old outcrops and relook at some of the outstanding questions that I had. And then conclude with some ideas about the implications for all of this work. And I guess it wasn't made clear. I think what we will do, just for the simplicity here on the format, is save questions to the end. So please, put them in the chat or definitely save them. I'm keen to have the discussion. I just feel like it's sometimes a little easier to ensure I get through the main body of the presentation if we hang on to them, because I will talk forever. I got to rein myself in. And if I have lots of questions, that gets me in trouble time-wise sometimes. So I appreciate that format. Okay, so part one. I look at what I call the multi-phase history of submarine channels from Cretaceous rocks in southern Chile. A number of sponsoring companies are at the bottom. This is part of what is the Chile Slope Systems Industrial Consortium, which has generally been funded by sponsors looking to apply what we learned from outcrops to subsurface reservoirs on continental margins, mostly around the whole world. And a number of collaborators, Brian Romans out of Virginia Tech, Lisa Streit out of Colorado State, and some others from across the US as well. And in this outcrop, you can see half a channel width, and just as a point of reference here. And there is a person here for scale. That is Andrea Fildani, formerly of Equinor. Chile is a neat spot to get to go for a number of reasons. It's a beautiful area, but it also has a really neat geological history. And I want to tell you just a little bit about that to explain why we go all the way there. It is part of the Andean belt. And on the left, you see the geological map of the southernmost Andes. The inset map kind of shows we really are at the bottom of the continent of South America. For anybody that knows this part of the world, the bottom here is Tierra del Fuego, and we have a nice fold thrust belt associated with Cretaceous, larger Cretaceous orogenesis. What's interesting about this part of the world is that in the Jurassic, there was a back arc set up here, a back arc basin, that caused, the extension caused the development of attenuated or thinned continental crusts. And off to the west of the study area, which is outlined here in red, we even have abducted ophiolitic material. Right? So that's all part of that early basin history. And so without that predecessor history, this really isn't that different than the western interior. In terms of the Cretaceous foreland. However, the difference here is profound in that predecessor history of a back arc on compression that followed in the Cretaceous, that thinned crust caused subsidence to really be exacerbated. So instead of this shallow forelands that we are familiar with in Western North America, that thinned crust caused some kilometers of subsidence. And as a result, we have over 5 kilometers of deep water stratigraphy in the foreland basin full here, all the way through the Cretaceous. It finally closes through a final phase of basin filling, and this Tres Passos formation is what I'm going to focus on, but it is linked genetically to this overlying Dorotea formation, which is a shallow marine deltaic system that kind of closes that deep water history of the basin before a major unconformity at the bottom of the Cenozoic. And so if just to give you a bit of the lay of the land on that stratigraphy, maybe I should point out again one more time here, with the exacerbated subsidence, the basin itself was what you'd consider underfilled. Any sediment came off of the fold thrust belt and the orogenic belt, and it came into the foreland, and then actually was filtered along a north-south oriented axial channel system, kind of ran subaqueously along the bottom of this basin for most of this history, right? And so north to south, you're looking at kind of the direction of flow for the most part. And again, looking at the Tres Passos to Dorotea formation, that's what's in this cross section. This is a north-south oriented cross section along the basin axis, and this would be a dip oriented section north 100 kilometers, this outcrop belt that we've studied thus far to south. The bottom of this zone here is what is the underlying Cerro Toro formation. The Tres Passos formation kicks in here, a lot of slope deposits, this brown color being mostly slumps and mass wasting and so on. You can see the scale here. This is 500 meters. So overall, our slope succession here in the Tres Passos goes all the way up. This kind of greeny color here represents the deltaics that prograde over the top. And you get a sense from this that indeed we have surfaces we can correlate from the deltaic top set off the shelf edge into the basin. And so what's kind of fascinating here is we have over a kilometer of mapped relief on these paleo slope systems. So it starts to behave from a depositional perspective a lot like a continental margin. These are really high relief slopes, nothing like we see in the Western interior because of that tectonic history. And what I'm going to be focused on today is in this black rectangle. And these are all slope channel systems. And as we follow them to the left, that's upslope, we can see an up-dip pinch out and eventually a tie to deltaic strata. And we can map this. And we're looking at 30 to 40 plus kilometers of offshore, distance from this kind of submarine fan channel system upward to the shelf. So it's a really unique place to be able to, look at these kind of linkages too. And so what does that look like when you're on the outcrop? A little confusing image. I'll try to explain it to you. This is a perspective image from Google Earth. The idea here is that north is down here in the lower left, and right, and the upper right would be south. And so paleoflow are these big white arrows moving along this outcrop belt. This outcrop belt where there's some white lines here at the bottom with the arrows, these are the submarine channel deposits. And then there's a huge recessive zone, a couple kilometers of stratigraphy, of slope. And then up here toward the top, these resistant units that actually define the Chile-Argentine border, those are the top sets. So in essence, we're looking at, and if I go back again, that's the transition from the slope sandstone, or the sandstone channels, the recessive slope all the way through here. And then at the top of the image would be the top sets. And that's what defines that border, as I alluded to, right? So that's way up here. And all that defines 2.5, 3 kilometers of stratigraphy. So I'm going to talk a lot about what's happening here above this lake. There's a lake on the landscape here called Laguna Figueroa. It's about 2 kilometers long. That's that scale bar there. All right, and you'll see I highlighted some stratigraphy. And the next image that I'm going to show, I'm standing here. Hopefully you can see where my cursor is spinning around. And I'm standing on the ridge to the left, and I'm looking down dip along that white arrow above the lake at this stratigraphy that is highlighted here with these large channel form like traces. And so if I take that next image, there's the lake on the lower right, Laguna Figueroa. You can see a highway along the side of that lake, and up on the hill slope, you see 2 what I'd call composite channel bodies. These are those slope system channels. And the white rectangle here, the lower channel body is about 130 meters thick, and the one in the upper left is about 110 meters thick. So these are composite features. And overall, we're looking at over 300 meters of channel stratigraphy. So you might imagine this starts to be the scale of, and the context of some of these reservoirs that we see in continental margins, like off of Angola, off of Guyana, off of Brazil, and so on. Very big, very sand-rich systems. And so if I now take a map, I'm looking down at that lake here. So now north is to the top of the image, as would usually be shown. Now, keep in mind, the paleoflow was from the north to the south. So along that outcrop up beside the lake, although it's all shortened, here they do look like nice channel form bodies. The outcrop exposure is one where the channels are coming in and out along dip when you get onto the outcrop, and that's what's expressed here. And so any individual channel kind of flows along north to south. It's exposed over multiple outcrops before it then dives back into the subsurface, making this a really nice place to 3-dimensionally constrain things like submarine channel fills. And on the right is just a cartoon of the channel as it's expressed here in the diagram on the left within this white rectangle. And so lots of paleoflow measurements to constrain which way it was going. And as you'll see, lots of architectural information that we pulled from the outcrop to understand the processes that were responsible for the products here. It's important to also notice that I showed those 2 composite bodies in that last image, right? They're made up of literally dozens of smaller scale channels. So the idea is you end up with a kind of a channel belt or channel complex made up of a series of smaller channel bodies. That's how they evolve through time and leave us with these kind of types of products. Quite a bit different in a lot of ways to what we saw in that fluvial system I mentioned earlier, but that's kind of the point, and kind of leaves us with some of the uncertainty we had in understanding what produces the products that we're looking at. So what do I mean by all that? Let me give you a little rundown of what this outcrop looks like to give you my backdrop and my perspective. All I did here is I've shown a red line pop up along the outcrop. The next photo I'm going to show you, I was standing just to the south of that, looking toward that outcrop. And in this outcrop, the flow is out of the plane of the screen toward where I am taking this photograph. So here's what I was seeing there. This is a channel fill. And you can see on the right, it's thick and quite sandy. As you move to the left, it thins out pretty dramatically. And you get lots more fine-grained material within the channel body itself. The bottom of the channel is actually defined by this white dashed line. And one of the things that you notice is there's lots of thin beds on top of the erosive base. which is a little counterintuitive if we're thinking of upward fining fluvial channels. These are different. And so what I identified or highlight here is that there's numerous incisions at the edge of these channel bodies, or what I call the margins. And you can already kind of see that. You can see little wedges of sediment, lots of erosion surfaces in here. And if I zoom in on this white box, you get a sense that there's an erosion surface, and it's draped by mud. And the notion here is that when you erode a deep channel in a deep water system like this, a lot of the coarse grain material is flushed through, and you're left with a billowing cloud of the fine grain material behind that kind of settles out and rains down and drapes the channel cut. So it's kind of counterintuitive in that the evidence for the biggest flows is often recorded by the finest grain material, but you can tell it's sitting right on top of what is clearly a nice erosion surface. So already some ideas that don't jive with what I normally think of as in a fluvial realm. All right, so again, same channel. I remember, if you recall, I was standing now just north of this red line. The next photo is going to be where that red line is. So same channel, except for now the flow is into the plain, opposite of what we just saw. Same erosion surface at the bottom here. Again, it's hard to see the edge of this channel. You'll see that in a moment. But you can see the transition from thick sand, largely pretty flat bedded here, if you notice, eh? And then it peters out and is eroded. And there's some erosion surfaces, and you get thin beds along the edge. And you also have thin beds along the bottom, right on top of that erosion surface. So in this case, if I zoom in on that rectangle, what I see is that there's that basal erosion surface, and then internally, there's all sorts of heterogeneity in this package, which is about 1 meter thick. Maybe the most obvious thing that stands out is this block of sediment, this thin-bedded block. It was on the margin, probably undercut, and then it dropped in and got incorporated into the base of the channel. And so that's basically a block of sediment falling into the channel. There's some smaller mud-clasty horizons that are dominated by sand. And then there's lots of other erosion surfaces within this whole package. And so the idea here is that we have this heterogeneity that with all these kind of key pieces of information, and the notion is that the channel served as a conduit for a long time. It was open, flows went through it and through it and through it before it finally filled, right? As kind of this channel form shaped body. And so this kind of drapey unit, as we describe it, draping the bottom of the channel body itself underneath here, kind of records that history of throughput, minimal deposition, bypass of sediment to the depositional probably lobes down dip. And so the last piece I want to show, same channel. Now we're looking at this edge right here where I highlight in the red, and this is where the edge of the channel is encountered before it dives behind the outcrop into the subsurface. And so it's the same channel is kind of coming around, and so we don't see the coarse grain material that would have been behind. It's behind the outcrop here, and this is just the thin beds toward the margin. And I show this just so you get a sense for the fact that we can actually see the bottom of the channels here, and it ramps up, and the edge of the channel is literally draped and then onlapped by these thin bedded materials. So we've got this plug of sediment that has thick beds of sand in the middle and these thin beds on the side. And here's some of those thin beds. If you looked at them in isolation, you might think, "Whoa, I'm in some sort of lobe environment." However, this is a really narrow and restricted environment. These sand beds, although they look like unconfined turbidites, are really only limited to a narrow range inside the channel at its edge. And so what does that look like overall? On the top, there's the lake. The channel comes out of the plain. I followed it along a few of these locations, and it dives back behind. And if I take observations from all along, this is a simplified expression of that channel here. And you can see there's the edge where all the thin beds were, down into the heart of the channel where we have that thick sand, right? But what we do notice, all sorts of evidence for cut and then fill in sand, cut and fill with sand, cut and fill. And that's the key, this polycyclic pattern here. We also notice that the sands and the fills are almost always flat bedded. They're not these deep erosional cuts over and over again, or there's not just one cut, as maybe I should rather say, with one big fill event. It's filled through a protracted series of cut and fill events. And so the whole outcrop, that's just one element, as I call them, one channel fill, one body that is made up by literally dozens of these things. And so that's how we get that overall stratigraphic picture of one element, sand in the middle, fine grained material on the sides, right? And there's a number of these all stacked together that leave us those stratigraphic products that I looked at above the lake. And so this is really similar to what we see in subsurface. This is a shallow seafloor image. There's the seafloor itself. And in high amplitude, you see this a graded stack of channel bodies, which I interpret here on the right. And that's not very far off from how we interpret what we see in the outcrop belt. These channels are on the order of 400 meters across, and they stack for up to 150 meters. Very comparable to what we see in the outcrop. And that's kind of what people got excited for in our consortium working in Chile, is that we replicate these architectures from continental margins all over the place, not just right under the seafloor like this one, but as at reservoir depth as well. And of course, this is not unique. So when we think of the fluvial system, we're targeting point bars over and over again. Not so when you look at these deep water systems. More often than not, you're looking at these isolated sand plugs, if you will, these channel form bodies. Hopefully, after walking through the outcrop, you say, yeah, I looked at one of those. You can see how that outcrop I showed was one of these channels. And this is simplified, but each of these would have those cut and fill events that I alluded to, a plug with sand in the middle and finer grained material on the edges. And so then the challenge is stacking these all up. But the key here is these are cylinders of sand, not these broad sweeping meander style deposits like we see in the alluvial realm. And so what are some of the key observations out of this outcrop study initially? We get these composites, coarse grained submarine channel fills. And these would be kind of cross sections that go through those. And I kind of showed you one of those from above the lake there in Chile. They define these elongate channel form sedimentary bodies. So they're kind of like half cylinders of sand, and they're all stacked on top of one another. Super common motif that we see all over the place. The internal fill is characterized by flat-lying stratigraphy. We highlighted that, with evidence for numerous incision events. So incision, fill. And what I do mention here is that there's kind of this master surface. That was the bottom one with that big drape on top. And then all the subsequent incisions are kind of subparallel to that master incision surface. This is a common motif, and there's some variability. You can see here there's sometimes some lateral stacking of the bodies as we see them inside the elements. Other times they're more aggradational and seem to be centered in the same spot and so on. But this is a motif that we see all over the world in these types of systems. And some of the questions are, well, what's the mechanism for the cut and fill? What's the mechanism for this cut and fill that we see within the channel form itself? And so that, we made the observations, but we're not very comfortable with that process-based explanation. So the fundamental question is, how are these channels maintained? How do they stay open through time? And then how do they ultimately fill up with sediment? And so we get these stratigraphic products to study an outcrop and or produce hydrocarbons from in the subsurface. So that's kind of where we left a lot of the outstanding questions. And then I got invited to take part in this cruise in Butte, and I'll explain what we saw there and then go back to Chile and try to make a link. And here, the key title here, sediment transfer through submarine channels via upstream migrating nick points. And although you'll hopefully, if you're not familiar with the term nick point, you will be shortly. A lot of great collaborators, different collaborators on this project. A lot of folks, marine geologists from the UK and Western Canada for the most part. And so this study that I'll show you is more a study of repeat bathymetric surveys, and I'll get to that in a moment. And so where are we working? We're in Western Canada. There's Vancouver. I'll point out first, probably the more common area. Maybe you've seen some studies out of Squamish. Squamish is a delta, a town just to the north of Vancouver, mostly linked to its popular ski resort Whistler, which is just next door. But it's at the head of this fjord, and these fjords, there's a whole bunch of them, have been really a target for lots of studies of turbidite systems because there's a huge eroding mountain range here, the Coast Mountain Batholith, shedding sediment at a tremendous rate into these fjords, which then of course means that they're very dynamic systems. We can watch things happen on a quite a quick interval. And some of the things that have been done, this out of Squamish, looking at the top of this image, this is a planform image. This is the delta lip or the delta front, and off of which to the bottom of the image, a series of channels had formed over time. And you can see what you're looking at is repeat surveys. They did a survey of the seafloor, then they did another one the next day, and then another one the next day, another one the next day. And in doing so, they look at the differences. Where did erosion happen? Where did deposition happen? And when they do that, they actually captured some really surprising results. And that is, if you kind of notice, there's some of these features look like they're bed forms, and they're migrating north or upward. They're not migrating down slope as we think of bed forms. They're migrating upslope. right? So really some surprising results that came out of these areas that have now really informed a lot of studies of deltaic stratigraphy and so on. And there's also this really fascinating look. This is looking down on the seafloor, flows coming from the top of that delta onto the slope, and you can see that monitoring the turbidity currents through these Doppler profiles, just kind of one of a kind sort of links between sedimentation events and the migration of bed forms, in this case upslope. So we're not studying, I'm not here to show you too much about Squamish. It's more just the example to demonstrate, hey, these is a pretty special area in terms of observing processes in the near surface products, right? I want to take you to Butte, which is one of the next big inlets up to the north. And why we like it a lot is it has this axial submarine channel that goes over 40 kilometers. So up at the head, this is just the bathymetric profile of this fjord. There's two deltas that feed into the head of the system, and they feed into a 40-kilometer long sinuous channel. And what I'm going to talk about are nick points. Nick points, and I'll tell you about those in a minute. They're spaced every 1 to 10 kilometers, and they migrate 100 to greater or to 500 meters a year. Migrating nick points, what is that actually about? Let me try to explain. And so what's fascinating here is a planform of Butte Inlet. And there's a channel at the bottom of that inlet. And there's its channel. There's those two deltas feeding in, and the channel runs along the central axis here. And on the right, I see two planform images, one here, obviously, and then the next one here is just interpreted. And so there's the channel itself. And this is the feature that I want you to see. This is a nick point. And all that is, if you think of a nick point, we're thinking like a waterfall. Water comes across, encounters a steep slope, and it goes over that waterfall, and on it goes again, right? And over time, that nick point will erode just from the water, the movement of water and sediment across it. It'll migrate up dip. And normally, we're thinking of them related to structural perturbations. I'm thinking of like Niagara Falls. In that case, it's bedrock. Here, these things seem to migrate rapidly. And so when we look at this map on the right, I show in 2008, that's where this map's from. There's where the nick point is. In 2010, it's migrated half a kilometer. 2015, it's migrated around this bend in the channel and further up yet. And so if I look at this red line, that's a cross section that I'm showing here at the lower image. There's water depth, 5 meters there. There's distance across the channel. And these are profiles of the channel through time. Green in 2010, 2015 in blue, and 2016 in red. And so what's happened in 2016, the nick point migrated across the zone of this red line. And so what it's done is it's carved a hole in the channel and got rid of other stratigraphy. So the notion here is that once it does that, it'll leave this series of cut and fills within the channel itself, right? Cut and fills that ultimately are just tied to the migration, the regular migration of nick points past this position. And so if I go back to the outcrop, another example, we've got our master erosion surface, some drape, and then a series of erosive cuts that ultimately lead this product we described with a sand in the middle, thin beds to the side. And this outcrop is the same scale as what I show here in this image in the bottom and the blue rectangle. So really kind of comparable, cut and fill, cut and fill. And we are like thinking, wow, well, maybe these nick points are the mechanism for the cut and fill that we've observed, but not been able to, we've observed the evidence of, but not been able to make sense of in the outcrops themselves. So let's think of these longitudinally along the channel. So these are not profiles, of course, across the channel. They go along these paths as I'm showing them here. And the nick points, as I described, it's kind of a relatively low gradient, a steep gradient, and a low gradient again. That's the nick point. That's what's migrating past. So time 1 would have been here in gray. In time 2, the nick point has moved from here back over to here. And in doing so, has eroded a bunch of sediment here and deposited sediment in other places. Right? And that's what can be characterized in difference maps. And so what this is on the left is a difference map over 7 summers. The channel is characterized by alternating segments of erosion and deposition along its length over this time frame. So there's the channel. You can see that, I think, quite regularly there. And basically, where it's white, you've added sediment over 7 years. And where it's dark, you've subtracted sediment. So through the migration of a nick point, you're eroding sediment and depositing it. Right. And so it's this fascinating setup where this channel is actually not just setting sediment from straight through it from maybe the delta to the submarine fan, but it's it's moving as almost a conveyor belt in these sediments that it keeps reworking within the channel itself. So what does that look like? Hypothetically, it starts with a nick point, flat, sharp drop, flat. That'd be time one. That's the nick point. But with time, flows come through, it erodes back, remobilizes this old sediment, and deposits it in this really flat lying thin body down dip. Step back once more, another body is laid down on top. So, you know, you can see how when this nick point keeps eroding, you're left with a hole, the black zones, and then you're accumulating sediment over time in these white zones. And that's what is happening in where I've kind of indicated in yellow. And of course, this happens multiple times as nick points migrate through over some period. And so what does that look like in the data? This is that same kind of longitudinal profile I indicated earlier around that channel bend. This one here that's in the white rectangle again. And so 2008, the oldest deposits versus then the last survey we have in 2016 implied here. And you can see then you're left with these wedges of sediment, 1, 2, 3, 4 over time, and you're depositing and then eroding. Depositing and then eroding. So you're left with this really dynamic channel system where the channel isn't migrating laterally very much at all. It's stuck in place. What's changing is the longitudinal distribution of sediment through time. And so one of the thoughts we had is, well, look at these bodies. What would they look like in the rock record where they're not very thick, they're really quite long, and they're relatively speaking, they're going to be pretty flat, right? They're low angle within the channel. And if you think about it, that's not that different than what I described from Chile. So the observations here that these nick points migrate up channel, and when they do so, they leave elongate, discontinuous channel-formed sedimentary bodies. So these are the discontinuous, they don't go the whole way. And they're channel form in that strike direction, what I'm not showing in this image, right? The deposits are what's left behind anyway is characterized by flat-lying stratigraphy. And of course, there's going to be evidence for all sorts of incision surfaces related to subsequent, every nick point that migrates is going to do some eroding. And then so that's your mechanism potentially for incising over and over again. And it's clear, though, that, again, the channel's not migrating back and forth too much. The subsequent incision surfaces, the nick points are kind of constrained to within the channel itself. So those subsequent incision surfaces are, relatively speaking, subparallel with that master incision surface. And if you recall, that's basically the observations that we described from the outcrop. So you can see where I'm heading. The prediction is that with a series of nick point migrations, channel fill will become highly segmented due to repeated incision. And you'll recall from the last time I went to the outcrop, I was focused on the strike view. I was kind of reconstructing the strike view, you know, the flows going in or out, in or out. What I'm going to show you now is we went back to the outcrop, and as if you recall, the outcrop is basically dip oriented over the length of it. You know, you remember it ran north to south, and that's also the orientation of the outcrop belt. So we have a lot of outcrop to look at that is oriented in a way that's kind of favorable for us to really pick apart these downstream oriented sedimentary bodies. So that's what I'm going to show you here. And I'm going to some technology here. This is actually a drone model. We flew a drone here to try to capture some of this subtle variability, because it's really hard to capture these things over kilometers. Some pretty subtle stratigraphy, as I'll show. But in this, in most of these images, I'm thinking paleoflow will be from left to right. All right, that's the key here. Another group of collaborators, this time some from both studies that I talked about earlier. So our objective, what is the down dip expression of submarine channel fill? And again, now we're trying to think, well, boy, we just saw what it looked like in Butte. If we want to prove or disprove that nick points are important, we should probably be able to replicate something like the stratigraphy we saw in the modern. Again, going back, you recall, paleoflow is along the outcrop, so north to south, and the outcrop is oriented in that direction. So what I'm going to do next, I'm focusing on this portion of the outcrop right here. And this is about a 3 kilometer long segment, where it's basically a dip-oriented exposure. It's flowing from left to right, right along the outcrop, so we can follow that. That's where I'm heading back. And so this is a perspective image of a portion of that outcrop. So we did a lot of photogrammetry modeling, putting together all these. So with the drone, taking hundreds to thousands of photos and bringing them all together in photogrammetry software to recreate these 3D models from which we can do all sorts of measurements, quantifying thicknesses and lengths of beds and so on. And you'll see how that works. And that goes beyond what we've started with these drones is getting a look that you never get normally. Just hard to see. And so some of the things we've picked out, I hone in on just an outcrop here at first glance. What am I looking at? There's some thin beds, some thick sand, not easy to see much. And if you were walking on the bottom of this outcrop, you'd be looking straight up at a cliff. We really couldn't see this outcrop particularly well. We needed the drone to get us out into space. And what I'm highlighting here is there's an erosion surface here and a series of beds that are actually angled this way. Do you see that? Flow is left to right. These are all back setting beds. And so what would that look like up close? Something like that, right? Remember that example I showed from Squamish, how those bed forms were migrating up the slope, kind of backwards from what we'd normally have anticipated. You know, we're always thinking of bed forms migrating down slope. You know, the modern says, well, that's not how they always work. There's a lot of them that backset and build upslope. And that's kind of what we're seeing a record of here, which is something we never really contemplated nor observed, partly because we didn't have these drones. Now, that's only just to show some of the power of the drone, I suppose. But what I really am excited by is this method we developed whereby we have a long segment of the outcrop. And we did this over that entire 3 kilometer long outcrop. And you can see here, we're looking at 30 to 40 meters thick. Okay, so there's a lot of sandstone packages here. You can see the vegetation. You know, it looks like any sort of photomosaic of an outcrop, if you will. But what we did in the software is we interpreted the outcrop like a seismic line. So for anybody that's spent time interpreting reflectors on seismic, you'll kind of go, I could see how you do that. Now, obviously, this is a lot more resolved. We're picking beds out and geometries out, so it's different that way. But it's the same principle. We're just tracing beds. And when we do that, then we can take all those beds. These are all in a 3-dimensional model that is, you know, geospatially, you know, intact. Then we take all these points and we project them onto a plane that's oriented, in this case, perpendicular or along the outcrop, which makes it ideal dip-oriented perspective. That's what we're doing. And so this is only from a segment of the outcrop. You see there's kind of a big divot here, a big erosion event or big erosion surface here. That's actually right here. Hopefully you're seeing my cursor okay. So this is much longer than what we see in this segment in the upper image, just for effect. But all the dots, these are all dots that basically that's how we've interpreted. And then we projected them here. And then on the bottom, we basically connect the dots, if you will, into the lines as the surfaces, just to mimic what we see in the outcrop. And you can see the colors here don't really mean much. There's to highlight that there's different bodies that are present and preserved in this dip-oriented profile within an element, within a channel body, right? And so if we hone in, this is that same image. Here's that, this cut again is that same cut. There's a significant cut here, which is up in here, right? And so when we look at these bodies along the length of this 3 kilometer long outcrop, and you can see this is this panel above here. Again, got about 30 meters here on the y-axis, and we're looking at 200 to 300 across, right, based on the scale here. When we take a look at this and measure and take measurements along the length of the entire outcrop, we see that the sedimentary bodies, and we measured 23 of them in this outcrop thus far, they're generally about 2.2 to 8.6 meters thick, and they're 46 to 450 meters long in that down dip direction. So that's these composite bodies that we map inside of an element. And so we think, all right, well, what is that? How does that compare to what we saw in Butte? Well, this is the lower part's a stretched out image, the same image we saw in Butte, only stretched out a little bit. Right, you can see that's back, sort of stepping back of all those bodies as the nick points migrated, and to scale. This rectangle is the same scale as this rectangle, and the same scale as this rectangle is implied. And again, just like you see here, this stepping of bodies upslope, we're seeing that here as well. Right, so our initial interpretations are kind of validated in that what we see in the outcrops, once we've been inspired to look at a similar way, is that there are elongate, discontinuous, channel-formed sedimentary bodies. That still holds. That's what we saw in the first place. But the deposits, yeah, they're what we said before, and we validate. They're largely flat-lying stratigraphy, but there are evidence for numerous incision surfaces. This new angle we took along dip, they're not all. They're basically the incision surfaces are all these ones. They're defining these different colored blobs as I've drawn them. Right. That's kind of how they've been manifest in that down dip direction. And the sedimentary units, you know, we got an idea of their width to thickness. And they're not that far off from what we see in the modern counterparts. If anything, they're smaller in the rock record, which kind of makes sense, because if you think of the modern, we're getting a snapshot in time, and with time there'd be some aggregation and more migration of those nick points, and we keep parsing and eroding segments and portions of those nick point sedimentary bodies. And in doing so, they would get more and more. They get smaller through time. So in the outcrop, we've gone the full gamut, and maybe we're seeing that product of a number of events. Whereas in the modern, we're not getting the full amount, which is probably why the bodies are thus far slightly different scales, and they're smaller in the outcrop. So lots to think about here, but hopefully you can kind of get a sense for how we've kind of come full circle and are trying to use the modern to better understand and fill in gaps and understandings of these really common ancient systems that we just haven't had particularly good understandings of. So some key outstanding questions. Are nick points important in all submarine channels? And I'm going to say, well, I think I can answer that to say, no, I don't think so. I think we do know point bar-like deposits. They do happen in deep water channels. I think we've seen, if anybody's worked on these systems, you say, well, I've seen a couple of those, and we do see them in seismic in particular. I haven't seen a lot of good outcrop examples, but there are some. But the question is just, where are they important? In which systems, and then eventually maybe we'd be able to link them to things like gradient and sediment supply. That's maybe getting down the road a little bit. We're getting there. And then if they are important, what are the recognition criteria? How do I know that they're there? And I think that's what we've kind of trying to demonstrate here through our efforts. Is it's been difficult. We wouldn't have been able to identify these things. I mean, the reality is that I've kind of come full circle, and more or less I've admitted here that we looked at the rocks, missed a whole bunch of, we got a bunch of good observations, but we missed a whole bunch of observations, had to get some information from the modern to go back to look at the outcrops. Without having that inspiration from the modern, we would have kept walking by and missing these key pieces of information. That modern key to the past is just so critical, and we just were lacking it until these recent data sets came to light. And so if I think about, as I wrap up here, some of the discussion and sort of implications, conclusions. So, this is it's not new that nick points have been recognized in channels, right? And submarine channels. You might not have heard too many of these, but yeah, when the places where they've been really kind of commonly recognized, places like West Africa, where you've got active salt in the subsurface, and it's rising, and the submarine channel is trying to cut down in response to that. Well, we've seen nick points be one of a key mechanism for that equilibrium profile to be maintained. We've seen when a meander loop is cut off, a big sinuous loop, it just doesn't break through. Rather, in a lot of cases, it starts and then it actually is exacerbated and achieved through a nick point migration. Kind of neat, right? So, but these are all perturbations to the system. See, the Butte Inlet observations suggest that nick points don't need any of those external sort of controls. They may just be a primary mechanism of submarine channel maintenance, meaning that it's just a conveyor for some reason, and this is definitely not understood yet. These nick points are just migrating like a conveyor up the channel over time. So the flows that eventually come down are just driving them and driving their movement, such that you think of like a fluvial system, and we're thinking, yeah, okay, well, you have a cut bank erosion and point bar accretion, and that's what keeps this whole thing in equilibrium. Well, nick points might be actually serving that same purpose of erosion at the nick point, deposition down slope of the nick point, and that in itself is what helps to maintain the channel, helps to keep the flows going, that it basically establishes that channel equilibrium. And so that's kind of our hypothesis, and it's very much so. There's no test here yet that we've been able to say, boom, this is it. But you can see where my excitement lies, and we might be getting there. And this hypothesis is that these upstream migrating nick points are actually primary morphodynamic agents in submarine channels, the equivalent of these point and braid bars in rivers. They kind of serve that same purpose, to keep that channel maintained, as in flowing, and then ultimately are a key mechanism for it to actually fill. So these are now ideas we're attempting to test, but of course it's a challenge without things like flume experiments and so on. But that's imagining where we're going, right? And so one of the things that I'm really excited by is, when you work hard on something and you make some great observations, you got some neat interpretations, you think, but then you reach an end, you're kind of like, well, okay, you kind of tail off in your description of what's happening, because you reach the end. You don't know what to do next. You got the observations, you're not comfortable with all the explanation of why, right? And so in this case, what I love about this model anyways, it can explain a number of the submarine channel fill observations that have been really hard to explain in the past, right? The fact that the bodies are always channel form shaped is in itself unique. The beds are not angled. They're not like accretion surfaces, right? They're all flat for the most part. There are probably some bed forms and so on that you can see manifest here, but these are not like pluvial deposits, right? And so some really interesting, kind of thought-provoking ideas to begin with. What we now are doing is thinking, okay, well, if this is true, we need to get the facies characterized. And this is not a difficult task in the sense that we've characterized a lot of submarine channels. And so my expectation is that, the facies for these are different than those. No, I think we've been probably describing the products of Nick point migration over and over again. We just haven't really realized that the driving portion of this product is Nick point migration. But if you think about an upstream migration is basically carving out older deposits, and they're slumping down and depositing rapidly just down dip of the Nick point inside the channel, well, that's going to leave us some pretty thick, maybe structureless sandstones. That's kind of really a common motif if many of you are familiar with sandy turbidites, right? So we are still now working on, though, how do the facies and the facies associations characterize? How do they link to the architecture? And that's something that is actually ongoing right now, and it's coming along actually quite well. And we're hoping to have a paper. Well, we'll see. We're going to get it out into review. We'll see if people like it or not. Lots of contentious ideas that are hard to prove when you're working on the rocks. But again, going back to this conceptual model, this is a BP model. They were, I think, in this case, inspired by reservoirs they had in Angola and in Egypt offshore, and they, of course, they identified that there are these half cylinders, half tubes of sand make up the reservoir. That's what they've applied to with these different colors, right? But exactly how they were deposited and then how they're all interconnected these are big questions that still determine the viability and production in these different places, different reservoirs like this around the world. Again, now some of these now are becoming more and more relevant to places like Guyana, which are hot even in these times. So the upstream migration model has a number of potential implications for the predictions of the reservoir presence, and of course then eventually the connectivity amongst these different sand bodies, right? And so I think from this BP model, like, it's pretty clear. You're like, yeah, well, we already knew they were stacked this way. That's absolutely true, but did we understand why? Not really. And what we also don't understand is that, we know that there's these segments of channel fills that have this half tube-like shape I've described, but they don't endlessly go the entire length of the slope. They stop. And exactly where and how? Well, that might be to do with more of that Nick point migration. Remember, I talked about how we had net aggradation in some segments, net erosion in the next. Well, if that gets manifest, we might be talking about how to define the up dip and down dip limits of reservoirs, including maybe trapping mechanisms within channel fills. And so lots of, as much as anything, just ideas that now are needing to be checked as we are inspired by these new observations. And so I hope you've appreciated sort of the way I've tried to do this through a kind of a retrospective look at initial ideas, inspired by the modern, coming back full circle, and then really leaving you with some ideas that I'm excited by, I feel pretty convinced by, but by no means are they conclusive, and we have lots of work to do to try to determine that. But it's kind of a fun place to be in this deep water realm where, a lot of our facies models for other environments are pretty clear and understood. Not so much here. We still got a lot of work to do, which is fun for a sedimentologist like myself. And so as I finish here, I thank my collaborators in the Chile Slope systems, in particular Brian Romans and Lisa Streit, my co-PIs, outcrop collaborators Jake Koval, Zoltan Sylvester from BEG in UT Austin, Zane Job from Colorado School of Mines, and then all the modern marine geologists that I've had, and modelers and so on that I've had a chance to work with, and lots of sponsors that have made this happen along the way. So with that, I am definitely keen to hear if you have any questions and try to defend some of the crazier aspects of my ideas. Thank you for listening.
All right. Thank you, Dr. Hubbard. A very interesting talk. Right. See, I got, I don't know if you can see it. We got one right now. Okay. We got one question that came in during the talk. Is the Nick point migration occurring suddenly associated with the mass transport of the sediment, or is it gradual erosion migration of the Nick point?
Yeah, it's a good question. So what we do know is it's probably fairly quick, and it's triggered by turbidity currents. And so up in the head of toward the top of the channel, up like toward the delta, there's a lot more of them, and there's lots of turbidity currents. So they move, annually, probably a few times, driven by turbidity currents. As you go way down the system, you have less turbidity currents that make their way down there. So there might only be one a year. But it's pretty clear that you need a turbidity current event that causes that local mass wasting, if you will, right? So it's kind of this mix of turbidity currents driving the overall process, but then you're seeing the slumping at the nick point head, which depending on the number of events over the year, how do you define gradual or punctuated? But I think normally I think of them as punctuated, associated with that passing of a turbidity current. And then if there's a number of them during, like in this case, the spring, when there's a lot of the melt in the high mountains, you get lots of currents coming through. It could even be daily. They're moving a little bit, so it can trend toward gradual if you think about it that way. But I'm thinking about the more, in general, as a punctuated sort of idea here. These things moving with important triggers.
So do you think it's do you think it's just a cleaning or a resorting process versus a primary depositional mechanism?
Yeah, well, I think it's all of those things, actually. I mean, I think I think of it that way, like that clean. I think I kind of like a maintenance, right? The channel maintenance. That's cleaning it out. But it also is probably depositing sediment where it needs to be deposited. When I say needs, right, in order for the channel to find that equilibrium profile, it's smoothing it out just the way it wants by depositing some sediment here and eroding some over here, and so on. So I think that it's part of that natural cleaning as you described it. But I do think it could be the primary mechanism for what we see in the rocks too. Just we weren't really thinking about it in terms of these nick points in the past. So kind of all of the above, if that makes sense. See, another question came through there from Ken Silver. 15 years deep water. Yeah, this describes the Kings Peak system perfectly. Cool. So one thing that's always, as Ken says there, the upper limit of the reservoir was a nick point, and that's awesome, right? As one thing that I think that happens a lot is some of these ideas that we eventually stumble upon as scientists. Somebody at a company knew about this, they never had the chance, nor maybe the motivation to actually share the information itself. But I think I'm not surprised to hear that the upper limit of the reservoir was a nick point. And maybe it wasn't one of these autogenic things. Maybe it was more of onto some topography or escarpment or something. But that's a good reason to imagine the up-dip pinch out of sands against some different lithology and so on. So very neat. I'm interested to hear that comment.
Have you been able to observe or just thought about obviously the sediment size and sediment range in different systems probably has an impact on nick point motif or nick point frequency and all sorts of things. So,
when you start to think about a model like this, which it's pretty early days, as I've admitted, right? There's a lot of work to do and to try to say, well, once you have that, well, here's the controlling parameters. And we're not there yet. So we've got two systems. Well, that's not true. The modern, now we've seen butte in this detail as they've shown here. There's been a few studies that come out recently looking at more like meander bend like examples, where you're looking at the reestablishment of a meander loops through a nick point migration and so on. And they've also seen some of these autogenic style ones, like ones that just seem to be flushing the channel and maintaining it, as we've discussed, in places like the Amazon fan. Like not all of it, not the procs, but certain segments of it. Like it's not Amazon, Congo, pardon me, the Congo system in West Africa. So it's not in the uppermost portion of the slope where they see this happening. They see it just landward of the big fan lobes at the end. So they're starting to get more and more data. So far, there doesn't seem to be, they're sand-dominated systems where they've been observed, I'll say that. What would happen if they were like conglomerate, like in gravel? Maybe that'd have a very different look. That's a good question. or mud-dominated, maybe they'd just be lower. Also, I could arm whip about that with no real good ideas. So much as I can say in Chile, it's a nice outcrop. It has the gamut. It has a little bit of gravel size stuff, but mostly it's sand and silt and mud and so on. So it's kind of comparable to what we see in Butte. So far the internal comparison makes sense, but that's still pretty limited.
Ken wants to be unmuted. I don't know if I can do that. Let's see.
Dr. Hubbard, you mentioned in your presentation about the drone work. It sounds like there was a lot of answers or a lot of questions that were answered by just using the drone work. Is that something that is now a mainstay in your workflow? Is going out, touching the rocks, and then also flying a drone just to get the other views? It's over the last couple of years, it's become real popular, and people are doing a lot more of it. So
it's absolutely. I think all of us use it, even just for photos and perspectives, right? That's what we've all been doing. I suspect to some degree. I've been really lucky. There was a PhD student working in the geography department here. It's more of a remote sensing type of project, but he was looking at acquiring these photogrammetry models with the science behind them, the best way to do it over vertical faces. And that led him to working with geologists and me and my group in particular. So yeah, in the last couple of years, he's become indispensable. Once he finished his PhD, I hired him as a postdoc. I'm like, I can't let you go yet. I need your ability. He's been kind of developing workflows for not just like for acquiring data that's ideal for what we do, but then also interpretive modules. Such that we can go in and actually measure things like I described today and so on. So it's like all of us, we're all kind of getting pulled into these different digital and data centric ways of doing things. And even myself, who's been just trained classically to spend time hanging on outcrop and measuring sections, the drones become indispensable. And now that doesn't replace, but it's a key part of the overall integration of the process for sure.
Okay, have you investigated into if nick points relate to lateral migration or sinuosity of channel complex?
Yeah, so far that's pretty hard. Haven't done a lot. We do see that they migrate a little bit lateral, but the question is, we've been watching the channel over 10 years of kind of, small, like nothing gigantic, right? And so what would happen if you had the outsized flow, the 1 in 100-year flow? Is that what dominates the stratigraphic record, right? And that's where maybe the channel does a bigger shift laterally, and then these nick points move in, and so lots of uncertainty. What's super interesting is this past winter there was a huge landslide in the catchment of this Butte Inlet, and it moved a tremendous amount of sediment right into the head of the inlet, blasted the delta in half. And now we're just now going out and we're doing another repeat survey to see what happened. What did it do? Did the channel migrate? Did you see anything more significant happen? Did it blow all the nick points away and they're all gone for a while and they got to reestablish? Lots to be answered there. Really great question though. You can see that now where we're needing to fill in all these different things if we're going to really prove this is a viable answer to some of these things we see.
Okay.
I'm reading some of those comments too. Some really good ones. Maturity of the Gulf of Mexico systems, the vintage seismic, pretty old. Would we be able to? Maybe we've missed some of these things simply due to their lack of resolution. I think in the lack of understanding, I showed you why my lack of understanding inhibited my outcrop interpretations. That's for sure, right? I had some limits. We didn't know what to look for. I think you're probably going to come across the lack of seismic resolution. Even the most resolved new systems are going to have a difficult time there, simply because a lot of times these elements are filling their sand on sand. So it's just not the lithologic contrast. So I don't know that we're going to be able to resolve this in seismic data the way we'd like. We will see the ones that are maybe more allogenic, like external, like escarpment related and so on. But
how do you think this relates to like historical models of backstepping, turbidite canyon or channel fill systems? Is this like the explanation for that model?
Yeah, I mean, it's always a challenge at the scale, right? I think a lot of this might be at a finer scale than what we're normally used to thinking about that way. But it's hard to know because now we are seeing because people are doing these repeat surveys and some of the more proximal things, and we do see this kind of retrogressive failure. That might be how we have thought about these things inside the channel as something like a nick point induces that or is part of that process. But yeah, I don't want to overstep my bounds. I've got a limit. I like to arm wave, but there's a limit there where I do think that the potential is there that explains a lot of the finer scale features, like the 15, 20 meter features and less. But to extrapolate it into big scale is still something that I think if we get comfortable at the smaller scale, then we got to start thinking about that larger scale and how there might be feedback between all that. So tough one, yeah, but that's a great question too.
Okay, well, I see Ken down there, but he shows he's muted.
Yeah, I'm trying. Is that
there? He is.
Yeah,
we can hear you.
Okay, excellent. Yeah, as far as the Gulf of Mexico, the type of channels varies tremendously across the basin. Kings Peak is over on the east side near the Cretaceous shelf margin, and so it's got a lot less salt underneath it than what you see in the other parts of the Gulf of Mexico in general. The nick points there were spaced, I'm guessing probably like 20 miles apart or something like that. And it would just create a little set of jewels going all the way down Kings Peak. There's a whole train of them that were entrained in the same channel complex. And like you said, they're pretty low sinuosity. These were like on the lower slope part of the basin. And so the systems seem to be fairly well entrenched. And so they were just basically relatively straight shots of sediment getting out into the deeper water. But these nick points were very critical to whenever the channel complexes were starved, that they would set up these reservoir complexes and provide traps for where you've got all these erosional updip limits. And there were several of these. But as you go over to the east and to the west, towards Mars and Thunder Horse, these are like huge fill and spill basins, and so they've got a totally different geometry with them, and they're further out into the basin as well. And so once you get into that environment, then you've got just a very different type of a fill and spill environment.
Yeah, those are what, of course, many of us have seen in the publications. I haven't seen the nick point thing, but that's fascinating. I really appreciate hearing that. Just it's an interesting idea, and then another piece of the information, because I think going back to the question about sinuosity, there's obviously sinuous bends in these channels, but overall the ones that we've talked about are relatively low sinuosity, and maybe that's going to be a key component to when these things are dominant and or not, right? And so the entrenched idea, we don't have that ability to really know that in the Chile example, but certainly in Butte, it's an entrenched feature too. There's some levee, but you clearly downcut as well. So really neat.
Yeah, further over to Green Canyon, you've got just these. Instead of maybe 2 or 3 episodes of salt extrusion, you get like 7 or 8, and so you have a lot more sinuosity developed in these canyon complexes as they snake around salt massifs and things of that nature. And so there you start seeing the effects of these meander belts developing, but you still get nip points developing on those systems as well. On the lower slope and in the upper slope, but once you get past that into the deeper water, where you get much more fan type turbidite, and we really didn't see that much evidence of nick points like way out. It was more of a you're just in a debris flow, a smooth kind of a laminar flow, more or less, as you get pretty further out, as opposed to the high turbidity mass waste that you see up further on the slope. So, but it's really interesting to see how you guys document this, because we could see it in the seismic data, but nobody really took the time to like model it and figure out where it's being erosive and where it's being deposited. But we could just see it on the seismic where it was, but nobody really just kind of documented how much erosion occurred versus how much deposition, which you guys have done a great job of seeing that over a short period of time. And so, but I mean, for us, it was just intuitive what was going on. We just never documented it.
Wasn't really part of the need at the time to actually share.
It's like nick points. Yeah, we see it, but it's just kind of the up-dip limits. We don't,
Well, thanks so much for sharing that. Every time you hear something like that, it does help to make you feel like you're, as a group here, we're going in some the right direction. Like we have it all sorted, absolutely not. But this can't be a one-off to be anything relevant here. We need to see it over and over again and build some observations. So
Right.
so thanks for that anecdote. It's really nice to hear.
You got it.
Any other questions or comments out there in the chat? Doesn't
yeah, well, it doesn't look any, but that was really good discussion. It was really fun to chat. So I just want to again make sure I get that chance to say thanks again for tuning in. That was a lot of fun.
Dr. Hubbard, I appreciated the talk. Very interesting. Thanks for taking the time to speak to us, and hopefully we get to have you on again for another topic.
Love to come find you guys down there in person one day. We'll see how it goes.
Yeah, that'd be great.
All right.
Thank you very much.
Thank you. Take care.
All right.
Bye-bye.
Bye-bye.